I am the director of CINA, and I'd like to welcome you to our results briefing today for the project Cross-Platform Cybercrime Detection on Interconnected Heterogeneous Networks. The researchers presenting today are Liang Zhao, Associate Professor, Department of Computer Science at Emory University, and Andreas Züfle, Associate Professor, also from Emory. A couple of words before we start. CINA stands for Criminal Investigations and Network Analysis. We are a DHS Center of Excellence hosted by George Mason University. Our mandate from DHS is to support the Homeland Security enterprise in countering transnational criminal organizations. DHS Centers of Excellence are managed by the DHS Science and Technology Directorate's Office of University Programs to conduct groundbreaking research resulting in rigorous, objective knowledge products and timely solutions for DHS components. What this means in practice is that George Mason receives annual funding from the Office of University Programs, which we then distribute to scholars and institutions at George Mason and all over the country, and in several cases in allied countries. And that includes the research that you'll hear about today. The challenge areas in research in CINA's portfolio include criminal network analysis, dynamic patterns of criminal activity, forensics, both cyber forensics and traditional forensics, and criminal investigative processes. Like most of our projects, today's research addresses multiple areas. In this case, criminal network analysis and dynamic patterns of criminal activity. In addition to fostering research, CINA's mandate includes conducting education and workforce activities, such as summer research teams, which are hosted at George Mason University, and brings teams of faculty and students from minority-serving institutions from around the country to Mason for the summer. We're excited to be in the final stages of selecting the teams for this upcoming season. And an internship program supported by DHS. We last year were really proud to place interns at DHS's Cybercrime Center in Fairfax. This year, we're looking forward to an expanded cohort of interns, as many as a dozen. And placing them at our close partners, the Cybercrime Center, and also CBP's National Targeting Center. If your component is interested in hosting interns, we do make placements outside of the normal summer cycle, and we would be happy to talk to you about your needs. CINA also hosts events and conducts outreach. We have an ongoing Distinguished Speaker Series. Recent speakers include Abby Stilianu from St. Louis University. In January, we had Colton Seal, former FBI agent and leader of the High Value Detainee Interrogation Group, who spoke on interview mindset on the 11th of March. And just yesterday, we presented Dr. David Mayman from Georgia State University with a talk on exploring evidence-based cybercrime research. He was interviewed by Ethan Burke from the Sycamore Institute. Ethan is an undergraduate student, and the Sycamore is the first foreign policy-focused and national security-focused think tank run entirely by college undergraduates. All of our talks are available through our website. The one yesterday is still in editing, but will be up soon. So if you're interested in reviewing our talks, please check it out. If you missed the talks, you will also be able to receive Ethan and David's talk through the Sycamore website, where they will be distributing it as short form video. Upcoming speaker, the last speaker for this academic year is Dr. David Kyle, University of California, Davis. He is a sociologist who studies transnational political movements, networks, and human smuggling. He's the author of Transnational Peasants and Global Human Smuggling and co-developer of the concept of cognitive migration. So a very topical presentation that will be on the 6th of May. So please mark your calendar. The best way to know about what CINA is up to is to join our mailing list. You can do that at our website, cina.gmu.edu. That's CINA with a C.gmu.edu. And you'll receive announcements about all our events. I should mention that CINA is supported by a DHS board of directors, some of whom may be on this call, who help us to ensure the relevance of our research and help us to identify champions and funding for transition. In addition to our cooperative agreement with DHS, CINA also has a basic order agreement with DHS, recently renewed for 5 years, which can facilitate transfer, licensing, and commercialization. And if you're interested in the research you hear about today and you would like to transition it to your component, our transition and impact manager, Stephen Self, can help set you up. Now, without further ado, I would like to introduce Liang Zhao and Andreas Züfle with cross-platforms cybercrime detection on interconnected heterogeneous networks. Andreas and Liang, please take it away.
All right, is everybody able to see the presentation?
Yes, looks good.
All right, yes, so let me take it away. What we are going to talk about today. So I'll start by describing the research problem that we are solving, and I'll give an introduction to our solution. And then Liang will do a deep dive into our technical approach. And then, yes, I'll take it back and talk about transition and yes, and argue why the work of CINA is now more important than ever, and how we can maybe humbly support future work. But let me start. Yes, so let me first start with a figure that was in our CINA proposal. So I'll tell you what we wanted to do, and then I'll tell you what we actually did. So let me look back at the title real quick. So the title is Cross Platforms, Many Words. The most important part is the cross platform, which I think is quite novel. The problem of looking at multiple networks, how they interconnect, and how to find malicious node not in one network, but across networks. And this is what we wanted to look at. So we wanted originally to look at two networks, as an example, Twitter and change.org. So you might know X, formerly known as Twitter, as a platform where you can tweet messages and follow people. And you might not be aware of the platform change.org. It does still exist. It's a platform where you can do petitions. And you can raise donations and you can raise signatures for a petition to make change. And what was nice back then when we wrote this proposal 4 years ago was that on change.org, they actually had a list of petitions that were shown to be fake or malicious, or the money wasn't taken for the purpose they promised to. And at the same time, we were able to look at Twitter and see what Twitter users were advertising these malicious change.org petitions. So our goal was to look at both, so look at the malicious actors on change.org, for which we had a ground truth, and also connect it to Twitter and see who tweets about these malicious nodes and how is the interaction between those networks. And the goal would be, well, we know some ground truth malicious nodes in one network. Are we able, based on that, to infer the malicious actors in another network? So that was the plan until things happened. Well, for these two particular networks, data became unavailable. So Twitter became X, and one of the things they did was turn off the developer API that allowed us to search for tweets, for historical tweets. That was no longer possible, so we couldn't crawl any non-trivially sized Twitter data. And change.org removed the ability to look at past malicious petitions. So we could no longer do that. And that caused a problem because we needed data. We needed data of two networks where we know malicious nodes in one network, so we can infer malicious activity in the other. So we changed the approach to a different type of data. And since Liang and I are computer science people, we looked at the networks of Stack Overflow, which is a forum where programmers talk about programming problems and help each other and often post links to solutions. And we looked at GitHub, which is a network of code repositories where people can post their programs and yes, and share the code for others to use. And on GitHub, there's also a repository of known malicious GitHub repositories. Malicious as in they might have security weaknesses, they might be actual viruses, they might compromise your data. So there are some of these GitHub repositories that are known to be malicious. And now we can look at the Stack Overflow network where people talk, where people share information. We can see which users recommend these malicious networks to then use the information of what are the bad apples on GitHub. Can we find the bad users in Stack Overflow, which are two different networks, two different users? Can we maybe link these malicious users? So that's the idea of the project, linking information across networks. So yes, just to put things in words, our goal is to annotate, to having knowledge about ground truth cyber criminals in one network. Can we identify cyber criminals in another network? It might be the same criminals, it might be others that are connected, it might be the accounts of people in one network in the other network, and so on. And yes, our goal is to find these nodes across networks. Let me also, before Liang does the deep dive into techniques, let me talk about the data sets that we've used. I've just mentioned the GitHub Stack Overflow data set, where we have GitHub users and Stack Overflow users, and we look at the links that they have to each other. But yes, having sufficient amount of data, especially ground truths on malicious nodes, is difficult. And this was the main problem in this project, getting large data sets of multiple networks that are cross-linked with a ground truth of malicious nodes. So to get more data, we also created our own data using agent-based simulation. So we used, and I'll talk more in the next slide. I'll show a little video of the simulation, but in a nutshell, it's a simulation where we have agents that follow patterns of life. They go to work, they go to restaurants, they meet friends. And by meeting friends, a social network evolves. Initially, people meet randomly, they become friends, friends meet again. So social networks evolve. And we can use this social network as one network, and we can use the network of who met whom, the physical network, as a second network. And then in the simulation, we can spread a contagion, think misinformation, think infectious disease. We can spread that across the networks. And this is what the simulation looks like. On the left, go simulation. Go. On the left, we have our physical network with buildings and roads. The little dots that are moving are the agents that follow their patterns of life, going to work, going home. And on the right, we have the social network between them. So the links and the nodes are the social network. And the dots that you see colored are infectious nodes. So we model we simulate the spread of an infectious disease here, where we have exposed infectious and recovered agents. And now we can observe how the contagion spreads across the social network and across the physical network, looking at the locations of the people. So this is the type of data, this is the type of simulation we use to generate large scale, not real, but simulated data. Okay, and with that, I'll hand it over to Liang to give you a deep dive on our technical approach.
Thank you very much, Andreas, for your introduction. So here I tried to formalize our so-called cross-network source localization problem into a more kind of mathematical setting so that we can generalize. So as has been introduced by Andreas, we pretty much want to locate the source of the, or say the culprits of the problem, right? Or say the starting of the bad information from the source network. Um, so then we can match what we observe in the target network. So this motivation, we believe, is very broad in the real world, where we usually observe some networks they are for dissemination, and some other network they are for content generation. And in order to identify those culprits hidden in those content generation networks, we will need to leverage those bad kind of disseminations that we can observe in the dissemination network, where we call it a target network. So more mathematically and formally, we are observing those infected nodes in the target network and use them to infer the source culprits in the source network. And this problem is highly challenging and currently has been extremely underexplored. And if you assume you will use like the traditional algorithms, or say like heuristic-based algorithm to solve it, there are going to be two big challenges. The first challenge is that this is intrinsically a combinatorial problem, which gonna result in exponentially expensive time complexity if you want to find out all the combination and find out the true combination of the cells. And the second problem is that every single node they have features, and their features can impact whether they're gonna be infected by other nodes, right? So and another important thing is that the source network, their nodes has their features, and the target network they also have their own different node features. So it is prohibitively difficult to predefine the diffusion process about how the node features can impact the diffusion of the diffusion process. So in order to tackle the first problem, we proposed to learn the embedding of the network into low-dimensional latent space. So instead of solving the original big problem over the whole large graph, and that command help problem, we solve the optimization in the low dimensional continuous numbers. So reducing that into gradient descent problem, that is very fast. Next page, please. Yeah, so as you can see that this is our encoding decoding process where we propose encoder to encode the original space, meaning the graph space, into the latent embedding where we denote it as ZFS and TS. And we use reconstruction error to learn the encoder and the decoder. Next page, please. Yeah, and after that, we proposed a new graph neural network to solve the second challenge, meaning that we take into the consideration of node features about how they can impact the diffusion among the different nodes by that, graph neural networks. And we propose the different graph neural networks for handling different diffusion patterns. One is inside the source network. The second is across source network and the target network. And the third one is inside the target network. And after this whole process, we are able to predict the so-called the site YT, right? That is the prediction of the infection situation. And we compare it against the ground truth observations, which is denoted by YT. And that is pretty much to minimize the error between them. And this error gonna be backpropagated to learn all the parameters inside the encoder, decoder, and the graph neural networks. Next slide, please. So once the parameters has been learned, we can use them to do source inference, right? So as you can see on the right-hand side figure, we pretty much try to permutate and search for the optimal ZF, optimal ZS in order to maximize the left-hand side maximal likelihood of objective. And as you can see, this problem is reduced down to gradient descent problem because the embeddings, they are continuous numbers, which accelerated our solving. Next slide, please. So until now, I have mentioned about our purpose of source inference, which is to finding out who are the source nodes, right? But later on, in our project, after we finish our first goal, we extended this purpose into a more challenging but also very interesting problem, which is to figuring out how those source nodes infected other nodes. As you can see from the right-hand side figures, um, so the source localization can be illustrated on the left small figure, where the light red is showing all the infected nodes, while the dark red nodes, they are showing the source nodes, right? So this can summarize our purpose of source inference. But in many applications, we want to know more details about how those source nodes infected the other, infected nodes, right? So that means we want to find out the paths of the infection, resulting in the propagation tree. So this problem is a novel problem. There is, as far as we know, there's no existing research on that, and we formalize it as a maximal likelihood problem by additionally considering the optimization of T, which is denoting the propagation tree we want to find out. Right? And that is pretty much a combinatorial problem, and we develop new divide and conquer, dynamic programming based method to find out the T based on the edge probability we're going to learn. And once we find out the propagation tree, we are able to further update the edge probability. And this process, as you can imagine, is like an iterative process, and we just iterate it until convergence. Next slide, please. So here are our results for our first research I have introduced, which is for the source localization. We pretty much calculated most of the popular matrices based on the different settings of our networks. And compared our method, which is called the CNSL, against the comparison method. And as you can see from the right-hand side tables, our method is outperforming all the other comparison method by a large margin. And also, we have tried also to remove the consideration of the node features, and we can see a performance drop, meaning that considering the node features are very important to infer the infection and the source. Next slide, please. Yeah, and here are the results for the second extension of the research on the propagation tree identification. And we have tested our performance of our method called the DIPT on different real-world data sets. And we have tested the path precision and the Jaccard index. And we can see that the performance of our method is largely outperforming all of the comparison method. And it is not surprising to us because this is the extremely underexplored area, and only our method is designed for this new problem. And at the bottom of the slide, we are showing some example of some identification cases, and all the curves, they are denoting the propagation tree identified, but the yellow ones are denoting false positive, while the blue ones are denoting the true positive. As you can see that our DIPT method is much better than the comparison method, the DDMIX and the DDMSL. Yeah, next one, please. Yeah, so Alice, you want to take over here, or okay, good.
Yeah,
thank you.
I will. Yes. So now that Liang did his deep dive, let's talk about potential applications, potential transition. So yes, lots of words on this slide. Yes. So we hope that the algorithms that we have developed, the research that we have done, might find applications in some of your applications where you actually have real data that, of course, we can't see, we don't want to see, but maybe on your data set, using our algorithms, you might be able to find sources of spread of misinformation, of money laundering across networks. And one thing that we've looked into with one of our PhD students, but we haven't published on that, was looking into financial transaction networks. And that has become a very important topic for national security. There was a White House report a while ago that said that, quote, 50% of the North Korean nuclear program is funded by stolen crypto and money laundered money from stolen crypto, and which means that these illicit transactions in financial networks are becoming a real threat to national security, and this is the reason why I said in the beginning that I think that the work that CINA has been doing for close to a decade is ahead of its time and becoming more and more important, especially with application and financial transaction networks. And we've looked at crypto transaction networks, which are public. We've looked at NFT transactions, which are public, with one of the students. But our big problem here is that we don't have ground truths. We don't know which transactions are money laundering, which ones are stolen cryptos. So we don't have a ground truth. Of course, we can simulate, but without knowing any ground truths, it's hard. But yes, this is I think, a potential direction that where the work that we've been doing, CINA in general, and our cross-network work in specific, could find transition for other stakeholders. Then, yes, for the work that we have done, it's really two main papers at ACM KDD, the flagship conference in machine learning and artificial intelligence. One was published last year, which was the first work that Liang presented on cross-network source localization. And we also submitted our work on identifying not just the sources, but the entire propagation trees. We submitted this work to KDD 25, which is currently under review. And yes, our algorithm is published, and happy to help transition if there is interest on applying our algorithms to your networks and across networks. Yes, then just to maybe start potential discussions, some clarification, some discussion points. So we feel that looking not just at singular networks, but looking at multi-networks, such as physical, cyber, and looking at the interconnections between them to follow the thread of malicious behavior across networks, I think is an important line of work with many applications. But finding data sets has been our challenge. We've used simulations to create these data sets, but there's always this problem that, quote, all simulations are doomed to succeed, meaning that, well, we simulate what we tell the simulation to simulate, and then what we do on the simulated data will work because there's no surprise. There are no unknown unknowns. But in the real world, with real financial transaction networks, for example, we don't know what to look for. We don't know what is malicious. We have no ground truths. There might be things that look malicious, but there is, I forgot the contribution. There is this problem that, quote, do not attribute to malice what can be explained by stupidity. So just because somebody wasted all their money on cryptos, it might not be money laundering. It might just be something stupid. In other words, we don't have ground truths. Even if we look at financial transactions data, we don't really know what are the ground truths malicious actors. If we had such a data set, we could do much more. And maybe one thing that could be interesting to DHS and other stakeholders is our work on simulation. We could do more of that. We could use our simulation to create a world like the simulation that you've seen, where we have a realistic financial transaction methodology, and we can simulate financial transactions, and we can simulate actual malicious transactions and money laundering in the simulation. That would give us ground truths, and we could use that to actually see what works on financial transaction networks as an example, which I'm using this example because it might be interesting to many of you. Yes. Then, yes, the second point I have here is that the work we've done specifically is finding the sources of the spread of malicious behavior, finding the infection trees, who infected whom. But we could also think of generalizing our work to find patterns in general, such as money laundering patterns. And with that, we are at our end. Thank you, everybody, for your attention. And let's open it for questions.
Liang and Andreas, thank you very much. Very nice, tight presentation of some really interesting work. I am happy to open it up to folks in the chat. If you'd like to type in your question, I'd be happy to read it off. We have a decent size, but not overwhelming group today of 32 folks online. So if you'd just like to raise your hand, that's fine too. And I can kick it off with a question. This is a softball, but what was the most challenging task of this work?
Yes, thank you, Brooke, for the softball. Yes, the data. So we didn't realize how challenging it would be to realize our vision of connecting networks without having, and our work is supervised. So we need examples. We need examples of malicious behavior, of malicious activities to learn from. And we did a lot of crawling of websites that tell us which ones are the malicious GitHub repositories. And we found a good number, but in order to train the models reliably that we aimed for, we needed much more data. And yes, finding this data manually was challenging. So this might not be a problem for some of the stakeholders who may have such data, but for us, that was the main problem, getting our hands on data.
Yeah, it's difficult to get labels also because our goal is to find out the source localization and also propagation tree identification. So in order to evaluate how good our identified result is, we need the ground truth of the propagated tree and the source. So that is also something that is difficult. Yeah.
Very interesting.
Mm.
I was impressed by your initial slide about sort of the pivots you've had to make as data sources have changed. And I'll also point out to folks on the line who are very familiar with CINA's terms and conditions and the conditions of our grant that this project began several years ago when our terms and conditions were different. I'm not fairly confident that we would not be working with Twitter data at this point. And so that indicates a change as well. But it also underscores something about CINA's work, which is that the methods that we are creating are often abstract enough and flexible enough that they can be used for a number of different applications and with a number of different kinds of data sources. The challenge then is to marry it up with folks in the components and to kind of make that leap of imagination to how we can apply these very powerful and subtle techniques to your data set. Great, happy to take any questions from the chat.
Mm-hmm.
Okay, so let me give you another one. Tell me about the assumptions implicit in your model.
Yeah, the
Yes,
assumption. Yeah, you can go. Yeah.
You go. Yeah.
Yeah, we need to make the assumptions. One is for the diffusion patterns. So for example, first of all, we need to, our method is designed for the network where there are propagation of the information. whether or not that is criminal, information or other kind of virus or disease information. We need to assume they are propagating, and also we need to further assume whether those impacted nodes gonna become recovered into uninfected or not, right? This also requires some assumption. We also have other kind of, we have done a lot of experiments and we have tested a different type of assumptions. And this is one thing. And another thing is that through the course of our project, we are actually doing things from easy setting to hard setting, meaning that we may have a tighter assumption at the beginning. So for example, at the beginning, we assume that we have the complete observation of the network and also the complete observation of the labels when we are training the model. But later on, in the later part of our project, we have relaxed this assumption into partially known. So we think this is a reasonable trajectory that can not only, it's like do a trade-off between feasibility and the power of our method. Yeah.
Thank you, Liang. We have a
Mm.
question from Jim Jones, our former director at CINA. He asks, can you say a little about the computational requirements and time required? That is training versus operation or scalability.
Yeah, that's a very good question. As we have, as I have briefly mentioned at the beginning, is like this problem in nature. It is a combinatorial problem. It was especially complex, but we reduce it into a continuous problem. So then we can enjoy gradient descent, which are, intrinsically linear time complexity, linear to the number of nodes and edges. Um, and we have further done some acceleration for the the inference phase by further reducing the search space, right? Because traditionally, if we directly do this combinatorial optimization on all the nodes and edges, imagine you have a large graph, then that's going to be very, very time consuming, even though you have linear time complexity. So in order to tackle it, we leverage graph embedding technology. We can learn the embedding of the whole graph. Suppose your whole graph contains millions of nodes, but the embedding may contain only 100 variables, and each variable is a real number variable. And you can see that this problem then is reduced into just hundreds like variables to search their optimal solution, which is much faster.
I'll add to that just to give some numbers, some intuition. So I remember for the source localization work, our students, the largest network that they worked with was, I believe, around 5,000 nodes, and it's a social type of network, so many edges, average degree maybe in the hundreds. So we might have hundreds of thousands of edges, and our source localization took a long time. Running on an Emory cluster using GPU, I think it might be in the scale of a day to run it. So scaling it up beyond 5,000 nodes might be a challenge, but well, we designed our algorithm to that being the largest network. If there was a larger network, let's say hundreds of thousands of nodes, then we could change the algorithm and go back to the drawing board and potentially find solution to scale it up.
And Jim follows up. Sorry.
Yep.
Jim follows
up
question. To ask whether the algorithm is parallelizable.
That's a very nice question. We have different ways to do the parallelization, like based on the data parallelism. That means we can partition the graph into subgraphs and solve each subgraph problem in different machines, right? And or doing the kind of the layer-wise parallelism. My group also have research on this direction. But for this project, because our graph size is fine. It's not that scale. My group has research on working on those millions of nodes and billions of edges, those scale of graphs, and we can apply those distributed computing techniques. But the key thing is that is doable, meaning that if we combine the distributed computing technique and our project, when we do have such large application, then we can do this integration.
Great, thank you very much. Thank you very much, Liang. Okay, any more questions from the chat? If not, I'll ask another one. Okay, so last question from me is, can you go speculate a little bit more about how the good results you've gotten from simulated data will generalize to real world data, which is often the biggest challenge we have with these kinds of projects in transition?
Yeah, I'll take that one. Because when I was speaking earlier, I already alluded to that problem. The problem that, well, in our simulations, we make all the assumptions, and there is no unknown unknowns. We might add noise, we might add some known unknowns, so there is unexplained variance, but there is no surprise that we don't even model. There are no unknown unknowns, there is no unexplainable variance. And that's why I said earlier that, quote, all simulations are doomed to succeed. Yes, and that makes it hard. And we looked at real world data, of course, GitHub and Stack Overflow, which did work. We had some results there, but we tried to generalize our work to financial transaction networks where there's just no ground truth. And it's really difficult to identify, just using common sense, what might be a malicious node, what might be a malicious transaction. And yes, so what I meant earlier was Hanlon's razor, the problem that do not attribute to malice what can be explained by stupidity. And yes, that's also the problem, that even if we could identify a malicious pattern in, for example, a financial transaction network, maybe something that in the simulation is a malicious pattern. Maybe in the real world, it's just somebody who makes really poor decisions, and it looks like it's malicious because he's wasting, and it looks wasting money, and it looks like there's money laundering, but maybe it's just stupid behavior. In the simulation, we don't have these surprises, especially surprises that we get from humans, which, can be very surprising. Yes. So what I'm trying to say is that it's really hard to assess whether our assumptions in the simulation can generalize to the real world without having real data to validate our simulations on. And yes, for criminal networks, it's hard, at least for us, to get such data. But maybe some stakeholders have such data and might be interested in not giving us the data, but applying our algorithms onto the data.
Terrific. Thank you very much, Andreas. And this, I'll just foot stomp that one of the purposes of CINA and the other centers of excellence is to serve as a hinge between researchers and components. We have the cooperative agreement, which funded this research to develop, to do more basic research and to develop these kinds of techniques and algorithms. And I'll repeat that we have a basic ordering agreement which allows components to write task orders. Under those task orders, data sharing can be negotiated. But more importantly, it allows a direct relationship between components and researchers, which would allow, for example, sharing real-world ground truth data sets that could be used to develop these techniques further. So please, if you are interested, if that sounds like something that your component could benefit from, please reach out to us, either to me or to our transition impact manager, Stephen Self, and we'll set up a meeting with this team to discuss next steps. Great. If we have no further questions, we like to keep these sessions tight and focused so that our DHS stakeholders can get back to their important work. And so we'll thank Andreas and Liang for your time this morning, for all the great work you've done on this project and your partnership with CINA. And we'll wish everybody a great day.
Thank you very
Thank you,
much.
everybody.